So this is turbulent flow. Okay? Don't forget to write down the limits. I may forget also to give them to you. So make sure you write the limits for laminar versus turbulent flow. Limits for Reynolds number. Okay? Range. The limits, I'm saying the range. So the Moody diagram has three parameters. Which are those? The Reynolds number is number one, the horizontal. And on the vertical axis, on one side you have the friction factor F, and on the right hand side you have what? Do we remember? E over D, the roughness. So relative roughness, let's write it down. Epsilon over D. Now, for a stainless steel pipe, I have to go back to look now the Moody diagram, and I will pull it up here, because that's the main reason that I'm doing this problem, is to go over a little bit the Moody diagram. So remember, the Moody chart has three axes, Reynolds number X and two vertical. Left hand side, friction factor F. Right hand side, relative roughness. So relative roughness is epsilon divided by D. Now epsilon roughness. I'm going to go now to this little table and I find stainless steel. How much is the roughness for stainless steel? 0.002 millimeters. So I'm going to write it down. Epsilon for stainless steel from table, okay, 0.002 millimeters. 0.002, okay. So 0.002 millimeters divided by the diameter. Now be careful. Hello. How much was the original diameter? 6 centimeters. That's what we had. 6 centimeters or 0.06 meters. Now, because this ratio should be dimensionless, I need to convert the diameter to what? Millimeters. Because this is millimeters, I need to divide millimeters with millimeters here to cancel. So 6 centimeters, how many millimeters are 6 centimeters? 60. So be careful of those things. I don't want you to know how to do the Moody diagram and then all of a sudden you miscalculate the ratio epsilon over D. It needs to be on the same units. Write it down if you forget it. So whenever you divide epsilon by D, you need to have the same units. So this is going to be equal to 3.333 times 10 to the negative 5. It's actually 0.00. This number, very small. 0 point, and then 4 zeros, 333. 4 zeros.
So when you give us a question like this, is that what you would ask us for, the relative roughness?
Luego que pongas
Is that what you
en
would
tu
ask in the
papel
question?
No,
para
oh, we
el
didn't write the questions, yeah. Okay. I'm sorry, I was trying to do the problem. Okay, yeah, I'm totally sorry. Sometimes I do it, I don't know why, I forget to ask you what they ask. Okay, pressure drop. Head loss. Actually, I will find head loss first, to be honest with you, and then pressure drop. And pumping power. To overcome pressure drop. I care mainly for the first two, but okay, the third one is also just a formula for the power and some conversion. Pumping power to overcome. So we need the pressure drop in the pipe, the head loss in the pipe, and the pumping power.
This
Yes.
Can you show us how you got the E from the table again?
The E, this table here.
Okay, it's from that one.
Yeah, there's a little table here, it says stainless steel and it has for different material, and you get the roughness 0.002. And by the way, this head loss formula, let's not forget, is F L over D V square over 2G. That's what we're trying to find here, the head loss. And then for the pressure drop, you use the other formula that I told you to highlight them when we were doing the lecture, which is going to be FL over D rho V square over 2. So you just multiply HL by the density. And you don't have G. So rho V square over 2. But to me, number one is head loss, then the pressure drop, then the power for the pressure drop.
How do we find friction number?
There is the thing. So we know the length of the pipe, it was already given to us. We know the diameter, we calculate the speed of the water earlier. We're missing F. And for that F, now we use the Moody diagram. This is the F.
Okay.
Okay? I'm sorry, now it makes sense the problem. I'm sorry, forget it. That's my problem. So, to find the F, you need Reynolds number in the x-axis and the relative roughness on the y-axis. So now we have to use those two numbers and see what's going on. So let's see. Reynolds number is 1.863 times 10 to the power of 5. So 10 to the power of 5 is here. This is 2 times 10 to the power of 5. So it's 100,000 and 200,000. We are what? About closer to 200, right? Somewhere here is 15. Now be careful because this is a logarithmic scale. And you know how logarithmic scales work? If you go from 1 to 10, what's happening in the logarithmic scale? If it is a regular scale, we have 2, 3, 4, 5, 6, 7, 8, 9, 10. But if it is a log scale, how that changes?
It's getting smaller.
Keeps getting smaller. So originally 2 is here, 3 is here, 4 is here, 5 is here, 6 is here, 7. I mean, now I'm off, but that's how it looks like. So the 180 will be closer to 2. And that should be an approximation. It's not a big deal. So it should be between those 2 points, somewhere here. So this is my Reynolds number. How much is the relative roughness? Yeah? I was 10 to the 6, I'm sorry, here. Here. Yes, you're right.
So
And-
can I see that?
Yes.
How are we reading it?
Eh?
How are we reading it? Our Reynolds number is 18,000, right?
18,000. No, this is 186,000.
186,000.
Isn't it?
Yeah.
1, 2, 3, 4, 5.
Oh. 14.29.
Okay, 186, 300. So, yes, so we should be around here.
Eso no está la.
And then the relative roughness, the ratio is 0.00040. So 4 zeros, it's here. So we are very low, to be honest with you. So we're almost like a smooth pipe. So we're getting, and now here is the problem. This line is your 0.012345 zeros, right? And this is 1, 2, 3, 4 zeros. This is a little bit more than 4, right? Okay. So this is 0.01. This,
those two.
eh?
We're in between those two.
Yeah, so what I will do here, I will use an imaginary line that starts from here and it's parallel to this one. Okay, because it's not a number like even number like those, it's in between. So imagine you have an imaginary line that it's a little bit above this. This is 1, how much do we have?
It'd be between the 1 and the
0,
5.
Yeah, okay, 2, 3, so this is
Yeah.
0.03, right? 4, so somewhere here, okay, you're right, somewhere here. So it will start like that, and then as you move, you see the differences reduce. So technically, even if you start somewhere here, you will still be in between those two. So now let's see, where are we now? I kind of lost. It's good to have a ruler with you in the exam, so to make it easier. So that goes here, and we said how much? How much is Reynolds?
Point zero,
No,
Four
no,
zeros, three,
332.
186, right?
86,000.
So this is 100,200, so somewhere here. So if I go here and in between, so I'm following this line now, so almost all those diverge here, right? So we're very close, so there's no big difference. So we are somewhere here. I would say .001, a little bit higher than 0.016. So and then this is an approximation. So from here your F is 0.0162. Actually, without looking actually the solution, when they use the formula, the value, so this is the Moody diagram, an approximation, Moody, and formula from that they used, and when I say formula, I mean the formulas that